A very good morning to one and all present here. I am Hardik Molia from Computer Engineering Department, Government Engineering College, Rajkot, Gujarat. I welcome you all for our webinar, A Journey from Matrix Learning to Machine Learning, with our invited speaker, Dr. Tanujit Chakraborty, sir. On this event, I would like to thank our invited speaker, Dr. Tanujit Chakraborty, sir, who is an assistant professor of statistics at Sorbonne University, UAE, for accepting our invitation and for being with us today. Sir is also an associate member of Sorbonne Center for Artificial Intelligence. He has completed his BSc from West Bengal State University, Kolkata. He has completed his MS and PhD from the Indian Statistical Institute, Kolkata. His research interest lies in statistical learning, time series forecasting, and statistical analysis of networks. His research work involves developing statistical methodologies for data-driven problems from various applied disciplines. He is also worked as postdoctoral fellow at IIT Delhi and IIT Bangalore. He had received the prestigious Emphasis Research Grant to work on deep learning. He taught as visiting professor as IIFT New Delhi and Exam University, Bhubaneswar. We are thankful to Sir for accepting our invitation and being with us today. Now, I would like to welcome our head of the Computer Engineering Department, Professor Dr. Chirag S. Thakur, sir, to share his views on this event. Sir, please.
I hope I'm audible.
Yes, sir, you are audible.
Thank you, Mulia sir. It is really a great honor to have such a profound academician and researcher as part of our 11th webinar under the banner of Supercomputing Facility at GEC Rajkot. I welcome one and all, and as Mulia sir very rightly said, sir has our today's esteemed speaker has illustrious career as a researcher, as an academician. So on behalf of the entire computer engineering department and supercomputing facility in particular, I welcome you, sir. Thank you very much. I really thank Professor Hardik Molia to be the driving force behind the entire concept of having this webinar series under supercomputing facility. I also thank all the committee members of supercomputing facility at GEC Rajkot to be part of this SCF, and it is really great to have such dedicated faculty in department who really runs the supercomputing facility with quite an impressive professionalism. I would not like to stand between you and such a esteemed speaker, but let me share two pieces of information. To all the members who have joined this webinar, I feel privileged to share that computer department in few weeks would be starting one minor degree under the AICT scheme in artificial intelligence and machine learning. So our college students will get benefited out of this minor degree or major program in minor degree or honors program in artificial intelligence and machine learning. And the second piece of information is that from 2022, that is this academic year, Government of Gujarat has given us another bachelor's program. So we are already running one bachelor of engineering program. It's called BE Computer Engineering with intake capacity of 120 students. And from this academic year, we would have another bachelor's program, that is Bachelor of Engineering in Artificial Intelligence and Data Science with 60 students intake. So computer engineering department would be having minor degree as well as this BE, AI and DS. So keeping this in mind, I think we would have a long relationship with our today's speaker, and we would like to have his inputs also while designing the syllabus, going for some kind of procurement, softwares and all. So we would like to invite today's speaker as advisor to this artificial intelligence and data science program. And with this little request from my side, I keep the forum open for our esteemed speaker. Thank you, Hardik sir, for giving me this opportunity to share this information with our participants. Thank you very much.
Thank you so much, sir. Now I would like to request Dr. Tanujit Chakraborty, sir, to please share his knowledge and experience with us. Sir, please.
Thank you so much for the nice introduction and for introducing me to your college. And I would definitely love to be part of the course on data science and artificial intelligence, as you asked. It would be a great pleasure for me. So let me share my screen and let's start today's session. Okay. Dr. Hardik, can you see my screen? My screen is visible, right?
Yes, sir, it is visible, sir.
Okay. Okay. So let me start from here. So today we'll be discussing about one of the very basic and interesting topic. I think to whom I'm presenting, all of you are engineers, could be BTech or MTech, any students. So during your first or second year of graduation, you mostly have encountered with the topics in linear algebra. Mostly during our school days, we are usually taught with matrices, determinants. Then during our bachelor's degree, we start with system of linear equations. Then we start developing up to it. So we go for vectors, we go for matrices, we go for quadratic equation, we go for eigenvalues, eigensystems, linear transformation, and some sort of bilinear algebra, to say a least. So all these topics, when we learn, actually, we don't actually follow the thing that it is going to be nothing but all the topics, all the components that we are summarizing there, they are going to form a very strong basis for machine learning. So today's talk would be a little bit of technical in that sense. Usually I prefer to give more non-technical talks to general audience, but since you are bachelor's and master students, and I believe everyone knows a little bit about linear algebra, so it will be a little technical, but I'll try to explain it in a easier manner. So we'll be trying to make a bridge between linear algebra and machine learning, how they are connected, what happens here, and how it impacts in machine learning, the way. So as already discussed, I am currently working with Sorbonne University and Sorbonne Center for Artificial Intelligence. And my research interest mostly lies in developing data-oriented machine learning models for various problems from epidemiology, economics, engineering, and other sectors. So if we have to go back to the root of machine learning, so if I have to summarize it into one slide, from mathematics, I'll be taking calculus, the whole calculus, the multivariate calculus, optimization, and related facts around it. And from algebra, I'll be taking linear algebra. So if you in case are learning mathematics and you have to come across abstract algebra, you might not be interested about that in case you are going for machine learning. So it mostly calculus and linear algebra are going to be very strong basis for machine learning. And even if you are a computer science student or electrical engineering or some other engineering students, statistics and probability is the correct foundation for machine learning. That's also another thing. Unless you have a good grasp of all these topics, after a certain time, even after coding a lot, if you are even a good coder, you have to stop somewhere. So my suggestion to all the bachelor's and master students are, in case you don't have a very strong background in all these 4 topics, you have a good, spend some more time with, say, there is a book called Mathematics for Machine Learning, which is currently the popularly used book, and this book is taught in Stanford and other places. Those who doesn't have a background in mathematics, they are taught with this book, and then they come to the machine learning and deep learning courses. So have a look at those books and then feel yourself more comfortable while developing the machine learning algorithms. So broadly today we'll be talking about three of the particular things, three of the interesting connections. So I'll first connect linear algebra with, I wrote statistical learning. So mostly statisticians, they prefer telling machine learning as statistical learning. It's like in a statistical way learning from data, right? So it's not a machine is just learning by himself. It's learning through the data, right? Through the experiences given to the machine and a lot of data, of course. So that's why I will connect from linear algebra with supervised learning to say a list. Then I'll connect with linear algebra with some application to image processing. And finally, I'll end the talk by talking about a very interesting example from spatiotemporal data analysis. And I'll connect linear algebra to that as well. So let's go to a brief discussion about what are the topics we have read in linear algebra, quick refresher course. And then we'll come to the application, how these tools that will be discussing, how they are going to be useful for supervised learning setup. So if we have to tell the importance of ML in machine learning, importance of linear algebra in machine learning. So in machine learning, what we essentially do, it's kind of a curve fitting, right? So we are given with the input set of vectors, we map it to our output set of vectors, and we try to work on various linear and nonlinear transformations. So this is a very popular meme from machine learning XKCD. So this is your machine learning system. If someone asks, yup, you pour the data into the big pile of linear algebra, then collect the answer to the other side. What if the answers are wrong? Just stir the pile until they start looking right. So this is how, like, from a very narrow perspective to look into machine learning, I should say. Though this is not fully correct, of course. Right now, many sophisticated tools have been developed. Many transparent, interpretable tools have been developed in machine learning field. Though this is one crude way of looking at it. So if you pour the data to the system, it will finally compute a lot of linear algebra and a lot of probability calculations, and finally it will provide you the output. Or if we have to look at how linear algebra is helping machine learning models, whenever we have any Twitter data, whenever we have the chest image data, whenever we have the heartbeat data, whenever we have any sort of cat, dogs, all those images data, we have certain pixel values. We use maybe some machine learning model called the very newest deep learning tools to convert it into a numerical data set and then try to work on the data set. And from the data, we try to make inferences. Just like when you start at the very beginning in the morning. So I'm currently in United Arab Emirates, and here the time is approximately right now 9:45 a.m. So when I always wake up, I always start with, okay, Google set alarm at this time. So how Google translate our native voices into its languages. So all these natural language processing tools, they use GPT or transformer models to convert them into the machine understandable languages. So all these things, all these transformations in image and audio and video processing are done by mostly the complementary tools out there is linear algebra. So this is why this session is going to be very useful, and also the knowledge of linear algebra will be very useful for you to progress in future in the machine learning community. So right now, I always learned something that if there is an elephant in the room, you should introduce it first. So the elephant here is linear algebra. So I know all of you know about linear algebra a little bit, but if we have to start from somewhere, so it's going to be a branch of mathematics where we are concerned about solving linear equations. So we are given with a linear equation, and it is something like sum over AIXI equal to B, say. And in vector notation, we can write it as A transpose X equal to B. And this is a particular linear transformation in X, right? And linear algebra is very fundamental to geometry for defining various objects like lines, planes, and notations. Just like we have a 3D plot given here, a three-dimensional plot in which you can see, you can identify lines, planes, rotation, everything within a single image out here. So a linear equation defines actually a plane of x1, x2, xn, the vector, the order triple to us, space, and straight line defines the common solution to the equation. So we are trying to find out a straight line solution to the given system of equations or given linear equations at hand. So in general, these are the very common standard notations that we come across while defining linear algebra tools. I think all of you are very much very much accustomed with this sort of literature. So there is something called scalar, which is nothing but a single number. So in contrast to the other definitions, vector, matrices, and others, which are usually the array of numbers, here it's like nothing but a real valued function or a real valued integer. So it's going to be, if you take it from x belong to Rn, it's going to be real valued numbers, and if you take it x belongs to some family of integers, then it's going to be an integer. Then we can define, after scalar, we can define something called vector. Vector is nothing but an ordered array of numbers. So if we represent x1, x2, xn is xcol, what we usually define in India. There are a lot of definition type of thing in literatures, mostly the representation. Mostly the notations we use, they are very familiar with the US notations, where Europeans use a little bit of different notations for most of these things. Notations means we write down xcol. So in Europe, nobody writes xcol. They write so x dash or something like that. So it's like a little bit of different notations in terms of books of linear algebra. So if all the elements of this xcol or x vector belongs to in N, so we can call that x is also in Rn. So it is a n-dimensional things out here. So if we think of vectors as points in space where each element gives coordinate along with the x-axis. So this is how x1, x2, xn are formed out. Then from the notations that we define, scalar and vectors, we can come to the definition of matrices. Matrices is nothing but a 2D array of numbers. So here, each element is identified by two indices. And for example, if we construct a matrix, we can write it like the first few component 2, 3, 4, 5 or 2 cross 2 matrix. Then 2 is the first row and first column and so on. So in terms of an image, if you think about this, a matrix. So if A has a shape of height m and width n of real values, just like if you take an image of my face. So if you take an image, say 200 into 200 pixel image, so it will be having the height 200 and the width say 200. So this is how a matrix is very important in terms of understanding images as well. If we have the definition of matrix, we can come to the next very thing is tensor. I think all of you are right now familiar with something called TensorFlow. So TensorFlow name comes from this tensor actually. What is tensor? A tensor is an array of numbers which are arranged on a regular grid with variable number of axes. So here we didn't define it's a 2D array of numbers. We have kept it the regular grid with variable number of axes. So if we have to define an array with more than 2 axes, so the matrix things won't be very much useful. Suppose we have an image. Image usually consists of red, green, blue colors, okay? Color images. So they are like aligned with each other, mapped onto each other. So an RGB image has 3 axes. Say. So the element I, J, K component for R, G and B of tensor are going to be defined by A, I, J and K. So this looks very technical, but if we plot it into we define some set of shapes based on these tensors, This will be the shapes defined. So 1D tensor looks like this, 2D tensor looks like this, and so and so. So tensor is like something like which will be very useful when working with any data. That's why the 2016 or 15 version was that time TensorFlow used to be the most popular thing when I was doing my PhD. I started doing my PhD, so not 2016, I guess, 2017 or 18. So then while we have matrix and tensor in our hand, we can define a set of operations using those matrices. So we can add them, we can subtract them, we can multiply them, we can divide them, we can do all these stuffs. Among them, matrix addition and matrix multiplication are the base things, right? So if we want to add two matrices with each other, the very first thing that is taught in the class, say in the 10+2 or bachelor's classes, that we add matrices to each other if they have the same shapes, and by adding corresponding elements, so we add from first with first, second with second, like that, values, and it should be having the same shape. Say M cross N matrices, two M cross N matrices A and B can be summed up in a C matrix. A scalar also can be added to a matrix or multiplied. We can multiply it by a scalar as well, and we can define something like AB plus C, where A and C are scalars. But how does it connect to machine learning? So machine learning people were smart people. They mostly statistician and computer scientists to develop the era of machine learning. So they tried to catch up all the things that are there from mathematics, and they also have defined some notation on their own. So just like a less conventional notation used in machine learning, which you may not be getting in mathematics books, are the vector adding to a matrix. In machine learning, we do these things, right? We do add a vector with a matrix, but if you tell this to any school level students or college level students, they won't be like very surprised, right? But in machine learning, we have defined these things, and we call this broadcasting. Since vector B is added to the each row of A, so we add B in the each rows of A in the matrices. So this broadcasting is possible in machine learning, which is very non-traditional thing in mathematics, of course. So that's how, like, in case you are studying linear algebra from a mathematician, they will be telling you all the traditional things. So here, if in case we are doing some, we are the person who works in machine learning, so we will be using the mathematics definition, along with we'll be defining some of the new things, okay? Then multiplication of matrices. So if we want to calculate a product C by multiplying two matrices A and B, in mathematics literature, we have A has to have the same number of columns as the number of rows of B. So suppose A is a matrix of M cross N, then B should be having the number of rows to be N to multiply them. So A is M cross N, B is N cross B. We may get a C matrix which is nothing but M cross B. This is the traditional definition. So in machine learning, what happens? The standard product of two matrices is not just the product of two individual elements. It's a product and then summation. You multiply row-wise and column-wise, sum them together and put it into the one particular component. Like you design one particular component in the matrix like that. But while we will be working with machine learning, we'll be redefining this, and what we mostly use is called Hadamard product. So Hadamard was a 19th century mathematician from France. So because like French people, because I belong to a French university, it's very unlike that. They more emphasis on mathematics. They don't like applied subjects. They are mostly mathematicians. The people who work in even machine learning, they work on mathematics of machine learning mostly. So Hadamard was a very famous mathematician who defined something new called Hadamard product. So if you have two matrices which is having the same components, just like M cross N, the height and width are same, then you can get a new matrix C which is also M cross N, where you make the product in such a way that suppose if we have A11, A12, A21, A22, B11, B12, B2, B21, B22, if you multiply these two matrices, you will be getting A11, B11 as the first component, the second component as A21 or A12 into B12, A21 into B21, and A22 into B22. Just like that. You don't sum them up, just like you do in classical mathematics literature. So this is what Hadamard product is, and this is very much useful. When we work with any images, we do this thing. We actually use Hadamard product instead of using the general matrix products, because we have so huge values that if we keep on producting them and adding them, it will be a very large sum value. So instead of doing that, we just take the first component, with first component, we multiply them, we get another value. And like that we do. So that's how Hadamard product is very useful in machine learning. So that's why I always tell, learning mathematics from mathematician is our next level thing, and learning machine learning from like mathematics from machine learning people is going to be, you are going to learn both the things actually. So this is a particular example from the Wikipedia that I presented here. Now, how these things are useful in machine learning. When we work with the machine learning problems, how these things that we are going to define here are going to be very useful to us. So based on the shapes of the tensors, we have using them, we can create a very interesting problem out here. What is that problem? Suppose we have a problem of working with an image data set, say the cats and dogs image data. So this data set is available everywhere in the internet. So you just go to internet and find out the very standard image processing data set. Is also available in scikit-learn and all this, PyTorch, all these places. So we essentially convert a vector x into another vector y by multiplying it with a design matrix or W matrix or weight matrix, whatever you call it. So we are given with a set of pictures of some cute cats and dogs. From there, we extract some features, and based on the features, we try to predict whether an image of, it's an image of cat or dog, or say sheep or other things or not. So essentially, we are given with the x values. We have to get some linear classifier, say y equal to wx transpose plus b, and getting this W matrix is the essential thing, and B matrix as well. So we stretch all the pixels into a single column, just like suppose if we divide this image, input image of a cat picture out there into 4 components. So suppose it's a 2 cross 2 one. So we get the first component, the first pixel value to be 56, the second pixel value to be 231, third pixel value to be 224 and 2. This is not usually done. Usually it's broken down into many pieces with all the unit vectors out there, unit matrices out there. So suppose from this particular image, we get a 2 cross 2 image, we get this particular set of vector, x vector like this. Our goal will be to get it transformed to a y. So y means it will be either cat score, or we will be calculating the score which will be referring dog or sheep. Say, if we get very low score, we call it as cat. If we get very high score, we can call it as dog. If we get the standard score in between max and min, we can call it as sheep score. So our job will be to finding out this W and B, right? That's how we work with all the logistic regression, k nearest neighbor, decision tree, neural network. All this can solve this type of problems, right? And if we define this same linear classifier with bias eliminated thing, then we eliminate the B component. And how do we work then? We just add, you just look at here, we just add the B component as another column in the W matrix. So we just put the B as a column and map it with the W matrix. So it has now, suppose it was M cross N, right now it will be M cross N plus 1. And then in the B matrix, we use another unit like 1 as a bias term. We introduce it to there in the X matrix. So The X matrix was 4 cross 1, and it will be right now becoming 5 cross 1 with a bias term introduced out there. That's why you see in neural network there is a bias term out there while designing the neural network. You have x1, x2, xn, you have all the set of hidden units, and there you introduced one term. So because you most of the time you define the classifier with bias eliminated thing. So this is one of the standard use of this matrices to understand the matrices and tensors using the image examples. Next, another thing we study in linear algebra called linear transformation. So linear transformation means we design a transformation like Ax curl equal to B curl, where A belongs to Rn, n cross n, and B comes from n-dimensional real line. So it take the values of real line from the n-dimensional space. So B belongs to Rn, and more explicitly we can write the following set of system of equations with n equations and n unknowns. And suppose we are given with this sort of equation, we can transform it into writing Ax curl equal to B curl, which is nothing but, in case of simple linear regression, we always try to represent y in terms of x. So y equal to a function of x, right, plus some error. So y equal to, if it's a very simple linear regression setup, we take y equal to a plus bx plus error, where we minimize the error to get the best possible value of a and b. Using matrix, we can also do the same thing, right? Using matrix, we can get also the same notations, Ax equal to b, which is nothing but b equal to y you take, and beta x equal to nothing but, beta is nothing but here x curl, and x is nothing but, if we map it with linear regression setup, x matrix is nothing but a matrix out here in linear algebra. So we can view A as a linear transformation of vector x to another vector b. I think it's going to be a little technical maybe because this talk is online. So when online talks happen, so that's a problem. I cannot interact with the students. I cannot look at their face and understand whether they're really understanding it or not. Maybe if you have any doubts after we will be over, after the session, please feel free to turn on your camera and mic and ask me. Okay. So sometimes we wish to solve this unknowns, just like Ax curl equal to beta curl is nothing but y equal to beta x. Okay. So we try to solve here x. There we try to solve beta for simple linear regression. So here we try to solve x when a and b provide the constants. So how can we solve it? The very easiest way, x is going to be nothing but a inverse b. But this is solvable when we know a inverse. And computing a inverse is sometimes going to be very difficult. Unless it's a very standard like square matrix of say 3 cross 3, 4 cross 4 like that. If it's 1000 cross 1000 or 1000 cross 5000, say an image, the inversion going to be very difficult. The usual matrix inversion tools, then we cannot directly employ. So during our bachelor's, we mostly all of us, we study the matrix inversion. This is a matrix inversion we mostly study in high school, I believe. And the Gaussian elimination, just putting the B vector into the A vector, just like what we did in the image example, bias reduction things, elimination thing. And we keep on reducing it into and get from A matrix, the I matrix, and then like we keep on reducing it using some row transformation or column transformations, and then do the Gaussian elimination and get the answer. So this is two ways of handling and finding the inverse in classical linear algebra. Whereas if you are a machine learning guy, say, so this is going not to happen. So all the mathematics cannot be directly put into the box of machine learning. So if A inverse exists, the same A inverse can be used for any given beta B. But A inverse cannot be represented with sufficient precision. It is not used in practice usually. The Gaussian elimination also has the difficulty because it's a order of n cube matrix. So for n cross n matrix. So we have to, like the order will be n cube. So it's a like polynomial order. So it's very difficult to handle. So numerically it's unstable thing. So what is the software going to do? What is the machine learning algorithm when we'll be trying to find out this inverse in machine learning? How should we be trying to do that? So there are various ways to do that. Maybe gradient descent is one way of doing that from optimization point of view. But from statistical point of view, they define something called least square method or the L2 like minimization method. That what does it do? So suppose in case of L2 risk minimization method, what we do, we are given with y, we fit a linear line and try to get the y hat, then we try to reduce the sum of square error. So residual sum of square, y minus y hat, we try to minimize this sum over this square, and by derivating it with respect to the parameters, we get the value of a and b. Just like if y equal to a plus bx plus epsilon, we get a is equal to y bar minus beta b hat x bar, and b hat is equal to nothing but sxy by sxx, where sxy is the covariance and sxx is the variance factors. So this is linear regression, right? The same solution can be given by linear algebra. Suppose we are given with a system x cal equal to b. Our goal is to find out x cal. So if we multiply A transpose out there at the beginning, this is the finest or easiest way to prove this thing. So how do we get x? A transpose A into x cal is A transpose B. So x is nothing but A transpose A inverse A transpose B. Now if you recall, what is the in multiple linear regression, if we have a setup y equal to x beta plus epsilon, beta hat is nothing but x transpose x inverse x transpose y. This is the answer we get from linear algebra as well, even if we don't do the standard least square techniques. So that's how, if someone learns linear algebra, they mostly do not need to do anything when the proofs comes in machine learning. So mathematical proofs will be very easy for you to understand. So right now, instead of solving x cal using the standard inversion method or Gaussian elimination method, we can apply this least square method and get the values of x cal. So that's what we do in standard techniques and standard literature, machine learning literature, and also one may use the gradient descent methods out there as well. So in easy sense, if we are given with this sort of problem, so suppose all of you are students here, suppose I take all of your IDs, I ask you the question that how many hours you study. So I think it's too much for a day, 10, 8, 5. So it should be the Netflix hours, right? That much. So hours you study, I get the information. Number of hours you play games or watch Netflix, Amazon Prime or something else. So there are some people, the student too, who does maybe for 20 minutes game playing, which is not true for most of you, I believe. It should be more than that. So, and number of classes you missed. So maybe during the online sessions you didn't miss anything. You should be turning on your video and parallelly you can play games and do other stuff as well. But during the class, maybe some of you offline class, you missed some of the classes. And based on that, I try to get your grades for computer science or machine learning course. If I am given with this sort of design matrix, so n samples, here 3 samples, 3 features, and we have the output value as grade. So this is a standard regression problem. This is the standard cup fitting problem, right? And for this particular problem, if you see, if we create a 3x3 matrix, if we write it Ax cal equal to B cal, X cal we can calculate using that particular idea of least square that we learned in the last segment. So this is how we solve the standard regression problem. Suppose here it's not the data, if we collect, it shouldn't be 3x3. I think in the college you have say 200, more than 200 students. So it will be a 200, like 200 cross 3 matrix in that sense. 3 columns and 200 rows. So another interesting thing in linear algebra, so I think I'm going a little slow. That's what always happens. So norms are another set of things that we define in linear algebra. And these norms are very much useful. To say a least, suppose using the norm we define the different cosine similarity, different similarity matrix. So we define the Euclidean distance, we define cosine similarity, we defined Mahalanobis distance, we defined Bhattacharya's distance, we defined Charnov things, all these things using the norms. And this is the basis of unsupervised learning. So if I remember the K-means algorithm when it was found by Lloyd during 1940s to 50s time. So he first came up with the idea during that time. So the first K-means algorithm, it simply uses, it calculates the Euclidean distance between the set of values and used to get the amount of K choosing by like trial and error and get the clustering done. That was the simplest algorithm, simplest K-means algorithm was doing that time. So KN and K-means, all of them came between 1940s to 1960s mostly. So I think K nearest neighbor came by 1952 by Fix and Hodge. They first came up the nearest neighbor algorithm, the first K nearest neighbor algorithm. So these are the things, all these things come from linear algebra. These people were so good in linear algebra. So there was something called norms defined out there, which is used for measuring the size or the length of a vector. Norms map vectors to non-negative values. So norms of a vector is nothing but the distance from the origin. Say we are given with x1 and x2 vector. If we calculate a diagonal like difference or say a difference between x1 and x2 vectors, we can compute it root over of x1 square plus x2 square, which is nothing but an L2 norm. So, but whenever we are defining such norms, it should satisfy the following condition. One is triangle inequality, another is this the multiplication with the scalar alpha, and whenever fx equal to 0, x will be the automatic solution will be x equal to 0. So these are the few things it should be satisfying, and these norms are very important because if we can, it is useful to get the distance between two vectors. So unless we know the distance between two vectors, we can tell whether they're similar or dissimilar, which is nothing but what we do clustering. Unsupervised learning is full of finding the different set of patterns in the data. So we are not given with any y values or any labels of the data. So without knowing the level, we try to find out, given the score of mathematics students and say computer science students, based on their scores, maybe the pure mathematics students are supposed to get less marks than computer science students, I assume. Then if the distance is very high, I'll be putting into either computer science or mathematics category. So these are the standard cluster analysis we do. So we can define L2 norm, which is nothing but an Euclidean norm, whereas which is nothing but Euclidean distance between the origin and any point x. And L1 norm is also very useful, just like in case you have learned some algorithms, shrinkage methods, lasso, or ridge regression. So these methods actually, ridge regression uses L2 norm, whereas lasso, the very famous algorithm by Hastie and Tifshirani back in 1995. Hastie and Tifshirani are those people who wrote the book Introduction to Statistical Learning and Elements of Statistical Learning from Stanford. So they defined, instead of L2 norm, they used L1 norm and proposed something called lasso, elastic net, which is very much useful in machine learning as well. And there is another L infinity norm. So L infinity norm, an example of an L infinity norm could be max norm, which is very easy calculation of maximum of xi. So how does this thing useful in linear regression? In linear regression, we are given with, we try to get y in terms of W transpose x, right? This is a simple linear regression problem where we are given with all the x versus y data set. Say we have only one x, only one y, of course. So we try to get a straight line which will be the best fitted line in such a way that it should be minimizing the residual sum of square error. So another way of looking at this problem from the nonlinear perspective is to construct a basis function. So basis function is the origin of nonlinear regression. So if we define something y equal to w naught plus j equal to 1 to m minus 1 omega j phi jx, where phi is the basis function, or which is introducing the nonlinearity in the thing. Otherwise, we'll be having w naught plus w1 x1 plus w dxd, which is linear in the parameters, right? So other than doing that, if we introduce some nonlinearity out there with the phi function, which is a basis function in machine learning literature, we would get this following framework. If we have this sort of framework, we can use something called loss function, which is nothing but many a times we define L2 norm as a loss function. Or we may introduce also another set of regularizers just like lambda and calculate this particular loss function and minimize the loss function to get the following weights wi's. So this is the standard way of defining it, which is nothing but coming from directly from the linear algebra. So linear algebra gives us norms. We are using norms to get this. And even using these norms, we can get something called cosine similarity, the product of two vectors, and also some of the other calculations of Bhattacharya's distance, other distance function, Mahalanobis distance, and which are very much useful in clustering, in classification, in various other disciplines. So unless you have a good idea of norm, then it will be very difficult for you to grasp those like complex mathematical structure of, say, Mahalanobis distances or Bhattacharya's distance or cosine similarity. Okay, and why they are useful? Because these norms gives us the difference between the size of the vectors. So if we have two set of features, we want to distinguish them. So the very basic way to understand is to find out the distance. So suppose two persons, whether they are very similar or not, just like twins or not, what do? We look at their face, whether my eyes and my brother's eyes, are they very same? My face and his face is same. My nose, my ears are very same or not? If not same, if there is a difference, say greater than epsilon, we tell we are not twins. Just like that, we do it in clustering. Very similar example in unsupervised learning. Now, using the norm, we can define the distance like this. And there is something which is used in machine learning, is called Frobenius calculation in minimization of Frobenius distance in case of machine learning. In standard machine learning, we always adapt, as I say, we always adapt the classical mathematics structures, and from there we keep on building, right? So norm was nothing but the length of a vector. The distance is nothing but the distance between two vectors. And based on that, we can define something called AF, which is nothing but very standard notation, which is known as Frobenius form. And then this is used in machine learning just like when creating the layers of neural network. So layers of neural network involve a lot of matrix calculation. So from X to Y, we go to Y by defining a function, which is nothing but we are given with set of inputs. We create a hidden layer. How do we create the hidden layer? We compute X, we multiply X with a sort of, say, particular parameters, W transpose. So we compute W transpose X, we do a lot of matrix multiplication, and also we do some regularization there. So because we are choosing all the weights, so we also use something called this regularization lambda over 2 W squared, say. Just nothing but if it is a L2 minimization case. So we minimize the Frobenius of weight matrices Wi, so norm of Wi over different L layers. If like first hidden layer, second hidden layer, like that. And we keep on minimizing this particular loss function JR equal to J plus lambda into mod of this. Like, so if it is F is nothing but F defines Frobenius norm. Okay. This is the definition of Frobenius norm, by the way. So that's how in neural network we construct different set of hidden layers. So hidden layers is nothing but some matrix multiplication going on out there, right? So it's a standard matrix multiplication. What do you do? So that's how it is very useful to understand this norm and matrix multiplication for us. Then another set of things. So this is the best way to understand it, this example. So we are given with the input nodes. We construct a V matrix, which is nothing but I naught into Wi's, I naught into W naught, say I1 into W1, and get this particular from input function to first hidden layer. Then another matrix we construct for going from hidden layer, first hidden layer to output layer, And that's how the network is built. And in the network, not only by doing that, we also incorporate one particular thing called activation function. Say we incorporate, it builds the nonlinearity. If we want nonlinearity, we need something called, say, logistic function, logistic activation, tanh activation, and various other activation functions. So this is the matrix multiplication that happens in neural network, to say. Now, I think I'm going very late, but anyway, I may take some extra 10 to 15 minutes, I believe. So how we map from linear algebra to image processing? Another thing we study in linear algebra class is called eigenvalue system. Eigenvalues and eigenvectors. I think eigenvalues are the most important thing in statistics and machine learning, most important. So if I have to say one most important thing, that is this. Given a particular, I think all of you know how to calculate eigenvalues. Given a particular matrix A, we calculate, if we write AX cal equal to lambda x cal, where lambda is the scalar term and x cal is a non-zero, say, vector and eigenvector. And then we can get the solution of this particular system by one trivial solution is x cal equal to 0. Otherwise, if we calculate date of A minus lambda equal to 0, we'll be getting non-trivial values of x as well. So this is how lambda is the eigenvalue and x cal is the eigenvector corresponding to lambdas. And this is not unique, because if x cal is the eigenvector, then beta x cal is also an eigenvector, and beta lambda is also another eigenvalue. So that doesn't have the uniqueness property though, but the calculations are very easy, right? So eigenvalues are eigenvector. I think all of your bachelors or even for some people in 10+2, they have done these calculations. So this is the standard way of solving this. By the way, while you're solving eigenvalue system, just like this date of A minus lambda equal to 0, the equation we get is called characteristic equation involving lambda and all the components of A matrix. The solution of a 2×2 thing can be done by Sridharacharya's formula. So mathematician has also a lot of contribution. Indian mathematician have a lot of contribution there. You know how do we solve this lambda square minus lambda into this plus a constant equal to 0 by Sridharacharya's formula, or by one of the very famous mathematician from India. So characteristic equation is used to solve this excess. So suppose we are given with a particular example of this, we can get the eigenvalues like this, we can get the eigenvectors like this. I'm not going to the calculations because this is what I usually do in classes. So, okay. So offline classes, to say. So I do think that you know the calculation, how to compute the eigenvalues and eigenvector for a given matrix. Now, let me tell you what is the physical interpretation of this. Suppose we have a correlation matrix A. So we have a lot of x values and y values we calculated. Suppose I calculated all of your heights and weights. And from there, I build a correlation matrix like this. So with x, the correlation is 1. X with y, the correlation says 0.75. And with y and y is nothing but weight and x is nothing but your height. So I write down the correlation matrix like this, A. From there, I can get the eigenvalues and eigenvectors, right? So this is the plot of your, a plot by doing some standardization, some different standardization from -4 to 4 or something like that. We get these particular values in the green box, right? In the green box in the image, you can see. Instead of working with this XY data of your heights and weights, whenever we have the correlation matrix, we can calculate only, say, by computing the eigenvalues, we can get only 2 values. So if you are a computer scientist, you know the things, designing of algorithms. Instead of restoring all these, say, for 200 of you, if we have all of your heights and weights, instead of restoring all this huge information, not huge for us, but try to think it like that, we restore only 2 points. That is nothing but the eigenvalue lambda 1 and lambda 2. Corresponding this lambda 1 and lambda 2, we can get the eigenvectors. And it will be very interesting to see that the error ellipse with the major axis as the largest eigenvalue and minor axis as the smallest eigenvalue presented in the picture out here. So this is the very easiest way physically to understand what eigenvalues and eigenvectors are doing. So if we have a matrix, say a correlation matrix, from any two or any three things, 3 cross 3 matrix, we can compute the eigenvalues, and instead of restoring the whole data, eigenvalues and eigenvectors suggest us in the ellipse what is going to be the major axis, what is going to be the minor axis. So that's the very easy intuition of eigenvalues, eigenvectors from the physical point of view, understanding point of view. If we have that, instead of restoring the whole data, say it's a 2 cross 2 data here. Suppose we have a high dimensional setup. We have lot of such axes. That's what we do in dimensionality reduction techniques by principal components. So the highest eigenvalue, largest eigenvalue, and corresponding eigenvector we defined as principal component 1. The second one we defined as principal component 2, which should be orthogonal and independent of the PC1. And we get principal component 1 and principal component 2 instead of capturing all the vectors, all the say features. So suppose we have a image with say 100 different features. We cannot work with 100 different features. Suppose we want to reduce the dimensionality of the feature space. Even we can put it into a particular principal component values, which could be 1-dimensional, 2-dimensional, 3-dimensional. The much lesser we will go, the much information that we'll be losing. So if we construct principal component 100 for 100 features, we'll be having the 100% R square. Otherwise, if we get say first 5 principal components, we reduce from 100 dimension to 5 dimension. Just like here, 2-dimensional things data we are given. If we construct PC1 and PC2, no information is lost. But if we go on for only one PC1, straight line direction, then we can understand this. And how this is constructed? By computing the maximum variance between these lines. So the first line PC1 will explain the largest variance, the second line will be replacing the second largest variance, like that. So from directly calculating the eigenvalue and eigenvector, we can calculate the principal components, by which we can come across a method called principal component analysis methods, which is a basic, very intuitive 1920s algorithm for dimensionality reduction, still used today. So these are the physical interpretation of these things I have already explained to you. So then we can come up something called spectral decomposition theorem. We can write any particular symmetric and positive definite matrix as a product of P lambda, capital lambda P transpose. But this is very crude thing because it is only useful for symmetric and positive definite matrices. So rather than this spectral decomposition, this is an example of spectral decomposition I have given. We define something more solid in mathematics and machine learning, which is known as singular value decomposition. Because this eigenvalue decomposition, it is not unique. So we go for a more robust thing, which is nothing but singular value decomposition for understanding this phenomena very well. So right now, let me define the singular value decomposition. And from there, I'll go to an example on image processing. And I have also given the codes. My student has given the code in her GitHub repository, which is already there. I'll be showing the link. Okay. So the singular value decomposition is like for any matrix. So when we get the data shouldn't be always a square matrix, right? So we will not be always calculating for 2 people, 2 different features, height and weight. For 200 people, we will be getting height and weight. So it's not a square matrix, it's a rectangular matrix. So for any rectangular matrix, we can express the rectangular matrix, say heights and weights of all of us who is attending this workshop in terms of a product of 3 things, where the first thing comes from nothing but a rotation, a stretch, or another rotation. In terms of if you are a very person, someone who understands vectors, so its first thing will be representing it in terms of a orthogonal matrix, a diagonal matrix, and another orthogonal matrix. Nothing but a rotation and a stretch. Stretch means the diagonal of component, say lambda, capital lambda m cross k, and another rotation, which is nothing but the opposite rotation or transpose rotation. Okay. So we can express any matrix, any particular matrix which is rectangular as a product of one particular orthogonal matrix, diagonal matrix, and another orthogonal matrix. And this is very useful in understanding many things. Why and how? So from this matrix, if we calculate A transpose, then we can get the eigenvalue and eigenvectors from there. Or A transpose A also we can get the alternative eigenvalues and eigenvectors of the another diagonal matrix. So not the orthogonal matrices. So this is very useful for understanding something called a matrix decomposition, right? A matrix is decomposed into elements, and where if we get the largest, if we get the singular values, we can understand the different properties of the matrices. Okay, so how this is calculated? If we are given with a matrix A, which is nothing but here a 2 cross 3 matrix, we can compute A transpose, from where we get the eigenvalues and eigenvectors, which will be, we can compute, which is nothing but U. U is the first, say the first orthogonal matrix. The rotation, the second rotation is V, which you can compute from A transpose A, and so on, so like that. So finally, we can write a matrix in terms of, say, orthogonal into a diagonal into a orthogonal matrix. And it is very interesting to see. It is better than eigen decomposition, because here we can incorporate any rectangular matrix, but mostly data are rectangular, data are not never square. We don't observe 100 features with 100 say rows, 100 for 100 people. We don't always observe the 100 different informations. So if we have this thing, so we define from here the singular value decomposition, and any matrix has a singular value decomposition. Any matrix can have this, and also this is very useful for understanding or computing the optimal low rank approximation of arbitrary matrices. It is very useful for understanding face recognition problem, eigenfaces, by calculating the difference between the different query images in the principal component state. Just like when you upload a picture in your Instagram or Facebook, it identifies sometimes the person from your friend list or from your follower list with the person is. So by doing this face recognition, we can use singular value decomposition very easily. I'll show you an example how to do this. And also image compression, another example. So right now, let me give the example of image compression. So suppose we are given, so I think all of you have some idea, basic idea about digital image processing, a little bit. So image is nothing but a representation of a real image as a set of numbers that can be restored and handled by digital computers. Suppose we are given with this, say, a black and white image, and we calculate all the pixels from the particular image from the each and every small square matrices or 1 cross 1 matrices, and we write down its values like this. So the first part is 148 is the pixel values we write. So all these pixel values from the image data we get out there, so which is nothing but a matrix, right? So just like based on the image size, so image size is nothing but the number of rows versus number of columns, similar to any matrix representation. Image resolution is nothing but the area, total area covered by the pixel per pixel. The number of color planes is nothing but grayscale image, it is 1. RGB image, it is 3 things interpolated on each other, right? Like put on each other. So this is how we do any image analysis. If we have my color image, it's nothing but RGB layers onto each other put together. If it's a grayscale image, it's nothing but one dimensional thing in that sense. So if we are given with any image, say we are given with this particular image, so we take our image and then use very simple singular value decomposition technique to compress this image. So just like an example could be, I think all of you use WhatsApp, right? So suppose I take a picture by a very nice camera, maybe Apple iPhone or Samsung S22. I take an image. The image always should be 4 to 5 MB image. Whenever we upload it into WhatsApp, have you ever wondered that the image size reduces a lot? Not size, actually the quality of the image reduces a lot, and it becomes, say, 100 KB. So 1 MB image is 200 KB. How WhatsApp does this? This is the example I'm going to discuss here. And this particular image of myself, along with all the codes that I'll be discussing here right now, are available in this particular GitHub page. And this particular slide I'll be uploading in my LinkedIn page by tonight. And I'll be also sharing with Dr. Hardik after the session is over. So you can have a look at this particular GitHub page, which is created by my student, Miss Madhurima, and she put all these images and all the codes out there for your easy understanding. So if we do the SVD on this RGB image, we try to compute from this particular image data set. We do the, suppose this is the matrix say, we compute the singular value decomposition of this matrix and we get a low dimensional representation of this. Suppose we do this, we get only the first 5 rank of the images. So if we observe this, the image will be very much blurred. So if we reduce a lot, if we delete many of the columns from there, it will be a very strong blur image from the thing. So what WhatsApp does, they actually try to explain the variances in the images by different singular values. So it will be singular values. That is a small mistake out there. So in the number of singular values. So most of the variance, if we explain by 35 singular vectors in the image, from doing the singular value decomposition, then we can tell a rank 35 of the image will be representing an image which will be of 100 KB instead of 1 MB, but will not be too much blur. Just like if you keep on reducing it, the number of single values, the image will be more blurred. If we take all the singular values, it will be the original image, and that's how we keep on working on that. So suppose this particular data is 200 into 200 dimension, the width and row. If we get all the 200 singular values by using singular value decomposition, we'll be getting the same image. If we work with only 50 singular values, it will be not so much blurred, but a very compressed image of size less than, size means the amount of storage it requires, say instead of 1 MB, it requires say 100 KB. So that's how actually WhatsApp works with their RGB image SVD. So they use more modern algorithms these days. So, but this is one way of doing this. You can also try to implement this SVD to compress any image and get the lower dimensional representation of very high dimensional images. So since I don't have, I'll take another last 5 minutes. Okay, I am already very late. So, so another thing, I'll just show you an example. How do you go from linear algebra to spatio-temporal data analysis? This is very useful because so there is right now something is going on everywhere. Even Andrew Ng, the very famous Coursera founder, Stanford professor, he always right now talks about AI for social good. So right now, not only will be working only for image and video processing, natural language processing, all these things are important, I should say. Another thing is important to restoring the earth, to help the nature or help humanity with the knowledge of machine learning to control global warming and to say a few things. Just like currently in India, a lot of things are happening, just like in Kolkata to say, I can learn from my friends from Kolkata, Bangalore. Currently the temperature is at least 50 years of highest thing, right? So why this is happening and how this is happening, all these things if we try to understand, we may use some sort of machine learning out there. How can we use linear algebra and machine learning to this analysis? I'll just discuss a few examples. So matrix decomposition, if we have 3 matrices A, B, C, if we want to write A in terms of B and C, product of B and C, this is very easy thing, right? Then A is almost equal to B, C is nothing but called a matrix decomposition for A. Some very promising machine learning techniques are based on this, all these unsupervised learning techniques based on this. So essentially, I'll just convert it into a spatio-temporal setup. What is spatial? Spatial is space dependent. Just like we observe the temperature, when you observe the temperature, we can record it over time. We can record it based on different region. Say the temperature currently in say Gujarat is not the very same as in West Bengal. or Bangalore. So we can record the temperature using different regions, say space for now, and different time in Gujarat temperature for different set of days we can observe. So graphically, we have a space, we have a time, and finally we have a space-time data, which is nothing but a matrix. And we want to decompose this matrix into space one and the time one. Say, more easy example could be this. So this is an extract from a very interesting paper by Valpola, Ocha and Ealing. So published in Neural Networks 2006. There talks about global daily temperature problem, where you have a temperature and the region specification, just like the geographical region of the place, the latitude and magnitude things. So if you observe this, this is nothing but a matrix with the spatial and the temporal values, and we try to predict the global daily temperature. Suppose right now we represent it into a temperature thing and the spatial thing. So global warming is something which is very, like last year, this year the person got Nobel Prize in Physics for his very interesting work in global warming prediction thing, right? From the physics point of view, they predicted global warming since 1980s. They are doing this. So if you want to come up with this particular images of the globe, different places images, and if you try to get the time series component, that is the temperature, and the spatial component, that is the region coordinates, you can have this set of C and B values. So that is nothing but A, which is nothing but a space-time thing. You can decompose it into B and C, B cross C, where B is nothing but the space matrix and C is nothing but the temperature matrix. So this is a very interesting way of thinking matrix multiplication. So here also, if we want to solve this type of image data from which we want to predict the global warming, matrix decomposition is the most useful thing, which will be reducing or decomposing the general space-time matrix into space matrix and the time matrix. Okay, so if we want to put this in mathematical way, suppose we are given with, instead of A, we are given with X data, where we have M columns and N rows, or N rows. So contains data vectors, say we have all the signals from which we can understand whether there will be the signals of maybe voices, the images or word histogram from the Twitter data, movie ratings, distances, all these things we observe. We can create a latent variable model X equal to WH, where W is nothing but the weight matrix or design matrix, and H is the latent variable or source variable that we observe. And typically here our task is to discover the optimal matrices H and W for the given set X. So if we have a space-time data, we can decompose it into space and time, then work on it. Work with this in a more robust way to understand the global warming problem. So this is one of the very interesting area right now. People are working on earth science and solving earth science problem, because instead of not only working on image data, NLP, improving those things also works, but right now AI for social good is the one of the major concerns for ML people. They want to work on something which is not only gaining the Google shares price or not only gaining the Tesla share price. You should also work for humanity, right? So this is one of the last thing which I thought I would talk about regarding the application of linear algebra in machine learning for AI for social good, that is global temperature prediction or the global warming problem. And the very last slide, this is the very last slide, sorry. So people will ask me what I should study to understand this mathematics for machine learning. The second book in the first row, second column, this book, Mathematics for Machine Learning, it involves most of these things. Okay, linear algebra, optimization, probability theory, statistics. It has all these things and it connects with this with machine learning. So unless you look into, if you are a computer scientist, it's better to look into these books rather than going through a very hardcore mathematics book, which will be not connecting you with those things, practical things. This connects actually with machine learning to mathematics. Then if you are an applied computer scientist or statistician, The Introduction to Statistical Learning is the book that you should be taking your hands on. If you like mathematics, elements of statistical learning, if you want to learn machine learning, you don't have too much time, you just have 7 days time, and you know mathematics for machine learning, then get your hands dirty with the book called the 100-page machine learning book by my friend Andrew. So he is a very popular guy. He's from Gartner. So he wrote a very nice book, and the deep learning book is by Goodfellow and Bengio, the group of people from right now they are in Canada, from Canada machine learning groups. And if you want to interested about how temperature forecasting and all these things, you should be having a look at the book by people from Monash, Rob and George. And there are various other books. Maybe the most recent one, another recent one, Sebastian from Wisconsin Madison, he wrote this book, Python Machine Learning, which is a really nice book, I believe. And also Andrew Ng wrote this Machine Learning Yearning, which tells us how to deploy this machine learning algorithm in business. So that's all from my side, and I'm very sorry that I have exceeded the time frame. Maybe I always do that. So thank you very much. If you have any questions, please feel free to unmute yourself and ask me.
Thank you so much, sir. Sir, your session was very informative for all of us. And because our primary audience is UG students, so this was very informative for them to understand the importance of mathematics while learning machine learning. So, sir, thank you so much for this session. Just a minute, sir. I allow them to post their questions in the chat box.
Yes, please.
Participants, there is one announcement. After question answer, we will share the feedback form link. So please wait for a while. Right now, please share your questions in the chat box. All of you can share your questions in the chat box.
Yes, please. Also, if they want, they can unmute themselves and us as well. So no issue with that.
Okay, sir. So participants, if you want to unmute and interact with sir, then please raise your hand.
Yeah.
So I will unmute you. Sir, let me brief the questions one by one.
So sir, let me first upload this particular PDF out here. Maybe that will be very much useful for them. What is the document update? I think by this, is there anything, any way we can upload any document out here?
Yes, sir. If you just drag it in the chat box, it would be sent.
Okay. Let me try that. So, just a minute.
Sure, sir.
Is it happening? I think there is a problem in uploading this. So maybe today, by tonight, I'll be sharing the particular document in my LinkedIn page. Maybe I'll just give the link of my LinkedIn so that they can have a look. So I can also read a lot of questions are there and a lot of feedback. Oh my God, it's coming so fast. Okay, so what is the difference between this eigenvector? So eigenvector and singular vector is nothing but in eigenvalue decomposition, like in general, if it is like very same thing, actually very same thing, but applicable for rectangular matrix. So for rectangular matrix, you cannot get the eigenvalues. You can get singular values. So square matrix versus rectangular matrix, very easily speaking. So then voice is not audible from last 5 minutes. Oh, okay. I think that's due to maybe internet. Use of matrix in daily life, that's what we discussed, right? When you take, suppose I want to solve this problem. So this is how we learn machine learning. So when I was doing machine learning for the first time, the first project I did, I used to wear a mask, like not marks. I used to put hands on my face and take the images, and without marks, I also take the images. And suppose my father used to have a shop. Okay, we used to have a tea shop in our home. Suppose my father, right now we don't have anymore. So if someone is coming in the shop with marks or without marks, how can we recognize? So we take a lot of images from my family with marks and without marks, and then create a classifier, nothing but using the matrix, right? Any images is a matrix, right? So from that matrix, if we do the singular value decomposition, you use the principal component and create a classifier set, or use a logistic regression classifier, which can detect whether there is a marks or not. And if we put the system in front of the shop and someone without marks is coming, then I won't be rude and tell them without marks, please don't enter. They will show their face and it will show tick as you enter the shop, cross you don't enter the shop. However, this is very much non-useful in India, because in India nobody is going to hear you. With marks, without marks, nobody cares. But in abroad, this is very much useful. Just like this, whatever you are doing in day-to-day life, whenever you are talking with Google, okay, Google set an alarm, how it is converting your words, your mouth spoken words into the computer understandable thing. It is actually understanding an array of vectors, right? So this is the use of matrix algebra in machine learning. And any more questions? I can say good morning. The conversation of machine learning is very easy. Can you please give the method which is available? Method. I already discussed about the method. This singular value decomposition method. This the matrix decomposition method, its application in spatiotemporal data analysis, the particular norm and its application in clustering, unsupervised learning. The other alternatives could be any matrix understanding from eigenvalue, quadratic forms, PSD, and all these stuffs. They have parallel relationship with the machine learning things. This is very easy and very easily understandable. And you may see one complex application to this is deep learning. So in deep learning, we actually do matrix decomposition, but in a very typical way. Very typical way. Usually when we multiply matrices, it has number of columns should be number of rows for the second matrix. But we usually don't have that in deep learning. That's why we use all the different new notations that we define for multiplication and addition in matrix algebra. Okay, thank you everyone. So for your comments, some other comments. Okay, thank you. Where is ML used in working sectors? Means working sectors, what do you mean? I don't understand that, but yeah, so it's everywhere. So there is no sector right now available in which ML is not used. From morning, whenever you get up to whenever you sleep, recommender system, if you buy a book, it gives you the suggestion of another book in Amazon or Flipkart. So recommender system, every day in day-to-day life, you look at in your mobile what will be the temperature tomorrow. That's also machine learning. We have a forecasting model which is doing that thing, and you see when there will be a rain or not. All these things are coming from the same things. I want to do something for the planet. I feel this is, yes, of course. Right now, AI for social good is something I told you really interesting, and not everyone should work on computer vision and natural language processing. Some people should be working more for the planet. So say global warming problem, say earth science problems, and all these things stuff as well. Thank you everyone who wrote informative session and good session. I think I can see a lot more questions, but I think Amal, I have some other things, other stuffs to do from 12:30 IST. So maybe if you have any more questions, I would love to hear it from you. Maybe over LinkedIn, you can ask me some questions. We can have a good discussion maybe, because a lot of messages is coming. Replying right now for all of them will take a lot of thing, and I have some other commitments after another 5 minutes. Okay.
Sure,
but
sir.
Thank
Sure,
you
sir.
everyone. Thank you
Yes.
everyone for attending, and maybe please connect with me, and if you have any questions, I would love to have a discussion with you, some problems, some interesting things. Okay.
Okay. Thank you so much, sir. I will share your LinkedIn link with participants along with their e-certificates.
Yes.
Sir, one more time, thank you so much for accepting our invitation. I request our HOD sir, Dr. Chirag Thakur sir, to please share his views. Sir?
Yes.
Hello, Dr. Chirag. Please say.
Yes. Sir, namaskar. Thank you.
Thank you so much.
Very knowledge enriching experience and very fundamentals delivered in very lucid way with great set of examples. So on behalf of each one of us, one more time, thank you very much. And we look forward for long association with you
Of
and
course.
your
Of course.
institute. Thank you.
Of course, we'll be in touch for the any advisory things and anything. I'd be definitely available.